Hey guys, we're back with our second lecture. The first one was on eigenvectors and eigenvalues and how to find them. And today I actually want to show you one of the things that we use the eigenvectors and eigenvalues for, namely diagonalization. Okay. Again, we'll go over just required skills. And honestly, this is a fairly simple use of these things. So again, we just need to be able to find eigenvectors and eigenvalues. Okay. And at the end, we're going to use this particular skill and tie this back in with differential equations, of course, since it's a differential equations course. Okay, so here's what we know. What I know is that in general, matrix multiplication is not commutative. In general, if I have some matrix A times some matrix S, this is not equal to S times A. It's just not true. Okay. In general, it's true sometimes if either A or S is the identity matrix, and obviously this is true, but it's not true in general. But while it's not true in general, maybe we can get close. Okay. So what if, hypothetically speaking, instead of A times S being equal to S times A, what if it was equal to S times B, right? And A and B are different matrices. This is not commutativity, but it's somewhat similar-ish. And if I suppose furthermore that S is invertible, then I can actually rewrite this into a much more well-known form. S inverse times A times S is equal to B just by left multiplying S inverse to both sides of this equation. Now, this is called matrix similarity. Okay, not same, but again, similarity. So we say that A and B are similar matrices if there is an invertible matrix S such that, well, this, right? Such that S inverse times A times S is equal to B. And we say that A and B are similar. And similar matrices tend to have some of the same properties. The one we're actually concerned about is that similar matrices have the same set of eigenvalues. They don't have the same eigenvectors, but they do have the same eigenvalues. Okay, we can prove this pretty easily. This is not a very difficult proof, so I'll go ahead and include it here. We obtain our eigenvalues from our characteristic polynomial, of course, right? So let's see. So we claim A is similar to B. We claim that A and B have the same eigenvalues, even up to multiplicity. Okay? The proof's fairly simple. I get the eigenvalues from the characteristic polynomial, right? Which is the determinant of, let's say, B minus lambda I, yes? So again, it's written weird, but remember this is a determinant of B minus lambda I, which means, well, it's a polynomial in lambda, right? And the roots of this polynomial, those are the eigenvalues of B. But if I make a couple substitutions here, okay? If I make a couple substitutions, if I replace, let's say I replace B with S inverse AS, of course, if they're similar, I know this is true. Okay? And let me go ahead and replace I, that's the identity matrix. I'm going to replace I with S inverse times S. I mean, anything times its own inverse is the identity. 1/5 times 5 is, well, 1. Okay? All right, fantastic. And now I'm going to do a little bit of algebra here. I'm going to do some factoring. Remember, matrix multiplication not commutative, so you got to be careful the direction in which you factor things out, right? So notice I have S inverse on the left of both of these. Lambda is a scalar, so these two commute. Okay, so I'm going to pull S inverse out to the left. Okay, this will give me the determinant of, let's see, S inverse times A. So I'll pull S inverse out to the left, and I'm going to pull S out to the right. Okay, so I'll factor S out to the right. Again, S is on the right, S is on the right. And what's left inside here is A minus lambda. If I take both S and S inverse out, that leaves the identity matrix again. And then using my determinant properties, I can just rewrite this as the determinant of S inverse times the determinant of A minus lambda I times the determinant of S, right? Now, we can finish this off just one more step. We do know from our determinant properties that the determinant of the inverse of a matrix is just the multiplicative inverse of the determinant of the matrix, right? So if the determinant of matrix A is 5, then the determinant of matrix A inverse is 1/5, right? So I know that the product of this number and this number is 1, okay? Which just gives me 1 times, of course, the determinant of A minus lambda I. And notice what we've proven. We've now shown that the determinant of B minus lambda I and the determinant of A minus lambda I are the same. These are the characteristic polynomials. And the characteristic polynomials are the same, then the eigenvalues are the same. Okay? So these are fantastic. Okay? Now what does that mean for us? How are we going to use this? Well, what that means is I know A is similar to every matrix which has the exact same eigenvalues as A. Well, yeah, but if I take a matrix and I put zeros everywhere, but I just replace the diagonal entries with some numbers, just as an example, some scratch work example here. So let's say I take this matrix, okay? So I just put numbers on the diagonals, a 2 and a 5. Well, what are the eigenvalues of this? Well, aren't the eigenvalues 2 and 5? Right? If I subtract lambda, 2 minus lambda times 5 minus lambda, well, the roots of that are 2 and 5. Okay? But that implies that there's some diagonal matrix, not just any matrix, but there's some diagonal matrix that A is similar to where the entries on the diagonals aren't just the eigenvalues for A. This is a process called diagonalization, right? It's finding a matrix which is similar to A, but that matrix is a diagonal matrix, okay? And for non-defective matrices, matrices that have enough eigenvectors, okay? For non-defective matrices, that's just a matter of finding the eigenvectors and eigenvalues. So let me show you an example, okay? Please be aware in most of these videos to try and keep the time down a little bit. I'm going to skip through any of the scratch work you should be able to do already. Okay, so let's take a small matrix here as an example. Let's say A is 3, -1, 5, -1. And again, I trust, since I know that you, -5 here, -5. I trust that since you have gone through the previous video, I know you've done the homework for eigenvectors and eigenvalues, I know that you can find the eigenvalues and eigenvectors for this matrix. So I'm going to write them down. Okay, so eigenvalue 1, eigenvalue 2, I believe it's -2 and 4. Let me check real quick. Got my notes over here. Okay, yeah, so it's -2 and 4. The eigenvector for -2 is 1, 5. Let me write that down. Okay, and the eigenvector for the second eigenvalue is -1, 1. Okay, so all right, so again, we learned how to take find eigenvectors, eigenvalues. I trust that you guys can find these things. So where does the similarity come in? Okay, so here's another matrix that has eigenvalues -2 and 4. just put -2 and 4 on the diagonal and zeros everywhere else. Okay? I'm going to call this B. Okay? So what I know that A has eigenvalues -2 and 4. I know B has eigenvalues -2 and 4 because I constructed it that way. And so I know A is similar to B. Now remember the definition, as long as there's an invertible matrix such that S inverse times A times S will get me to B. So where do I find the invertible matrix? Where do I find S? That's typically the biggest problem when it comes to defining similarities. So where do I find S? S is the matrix created from the eigenvectors. Okay? I'm going to use these eigenvectors as the column vectors for a matrix, and that's going to be S. That's going to be the matrix which defines the similarity. Now, quick question. Does the order matter? Yes and no. The order didn't matter for these eigenvalues. I could have put 4 here and I could have put -2 here and it wouldn't have made one lick of difference. But once I've made that choice, my choices for S have to be the same corresponding choices. So what I mean by that is, see, I put -2 in column 1, and that's fine, but that means then that the eigenvector which corresponds to -2, that'd be 1, 5, that has to go in column 1. Okay, and for the second one, I've got -1, 1. Again, that's the eigenvector associated with the eigenvalue 4. That's got to go in column 2 because I put the eigenvalue 4 in column 2. Okay, you guys can find the inverse of this, but it's an interesting thought question. Do I know this is invertible? How do I know this is invertible? Okay, well, remember, the eigenvectors for a matrix are always linearly independent, right? Yeah, so I know these two things are linearly independent, and because I know that these two columns are linearly independent, I know the rank of this matrix is 2. Since it's 2 by 2 and it has rank 2, it must be invertible. Okay, you probably should find the inverse of this, and then just check to see that S inverse times A times S does in fact equal B. You can pause the video here and actually try it yourself. Yeah, none of you did that. God damn it. All right, fine. All right. Well, let's move on. I'm going to do one more quick example, and I'm going to show you what we're going to actually use this for, because what we didn't have here is we didn't have any eigenvalues of higher multiplicity. Yes. And now in the previous video, we did an example of a matrix that had eigenvalues with higher multiplicity. They didn't have multiplicity 1. Okay. Now I'm going to use that exact same example. So I know you guys have it in your notes, or worst case scenario, you can look up the previous video so you can see the actual methods for finding these values. But the matrix was 3, -1, 0, 0, 2, 0, and -1, 1, 2. Okay? And what we found was that they were 2 eigenvalues, specifically 3 and 2, but eigenvalue 2, this one we actually got twice. Okay, so this one had multiplicity 2. I got this one 2 times. Okay, all right. So the eigenvector associated with 3, again, I'm always guaranteed to get 1, at least 1 eigenvector. Okay, the eigenvector for 3 was 1, 0, -1. And for 2, I actually got 2 eigenvectors, okay, which is good because that means this is non-defective, right? This is non-defective. Okay. The first one I got for 2 is 1, 1, 0. And the second one I got is 0, 0, 1. Okay. All right, so I've got my eigenvalues and eigenvectors. And again, I can easily create a diagonal matrix which has the same set of eigenvalues, right? I just need to put a 3 and 2 2s on the diagonal of a matrix. Now, does it matter where they go? No, it doesn't matter. As long as there's 2 2s and a 3 on the diagonal of this 3 by 3 matrix and you put zeros everywhere else, then it's going to be fine. Okay, so I could put 2, 2, and 3, or 3, 2, and 2, and just because I feel like being different, I'm going to put a 2 first, a 3 second, and a 2 last, just because, right? And everything else in here is a 0. All right, now, how do we define the similarity? How do we find the S, the invertible matrix which defines the similarity? Well, that's not terrible either. Okay, again, I'm just going to use the associated eigenvectors here to make the column vectors for this matrix. Okay, and again, I get a little bit of freedom of choice here, not much, because remember it has to correspond to the same values and the same positions I've previously chosen. The eigenvector associated with 3, I put that in column 2, so this one I know has to go in column 2, 1, 0, negative 1. But both of these vectors correspond to eigenvalue 2, so does it matter which one goes where? No, it doesn't. Just, stick them somewhere. You do have to use both of them. You can't use the same one twice. That won't work. Okay. But yeah, so that works. Or you could have swapped the last 2 vectors I put in. Yeah, so this diagonalization is not bad. This is just something that you can sort of freely do once you have the eigenvectors and eigenvalues of your matrix. Yes? All right, now, how does this relate to differential equations? Okay, well, so we've done systems of equations and we've done differential equations, and I know what you're thinking. Like, you would really, really like to do systems of differential equations. Yeah? Okay. We're going to do that. Systems of differential equations. Okay. So let me put a system up here real quick. Okay. There we go. Put a system up here real quick. And we're going to talk about the solving strategy for it. But let's see. We've got x1 prime is equal to 9x1 plus 6x2. Okay. And x2 prime negative 10x1 minus 7x2. Okay. Now, I don't know what the independent variable for these is. Maybe x is a function of t. It doesn't really matter. We'll use t, but it's somewhat arbitrary. Okay? And the problem I have with solving this is that while this sort of looks like a first-order linear differential equation, I have this extra function in here, right? Yeah? That's not, that doesn't work, especially since x2 is definitely not the independent variable for x. It's not like having y's and x's in the same equation. So what am I going to do? Well, the first thing I'm going to do is I'm actually going to rewrite this, okay? If I write the coefficient matrix here, like we normally do with systems, if I write my coefficient matrix and I claim that A is 9, 6, negative 10, negative 7, right? That's literally my coefficient matrix. Then I claim that I can actually rewrite this system, okay? This system is actually A times x is equal to x prime, okay? Where x is the variable vector x1, x2, and obviously then x prime is just the derivative of those. And you can actually work out this multiplication. It works. So I take A and multiply it times x. That's 9 times x1 plus 6 times x2. Row times column. I get the same thing that equals x1 prime. And this is fine. This is another way of representing this, yes? Okay, now I'm going to make a substitution. And very specifically, I'm going to make the substitution. I'm going to let x, the vector variable, be equal to s times y. And I have a specific requirement for s. I want s to be invertible. Hopefully I'm kind of telegraphing where this is going by mentioning it's s and also that s is invertible. Okay? So let's say S inverse exists. Okay. Okay, so if I make that substitution, let's see what I get. I get A times sy, okay? And of course, x prime, well, the derivative of this, if S is a matrix with constant coefficients, well, the the derivative is scalar invariant, right? So we just factor that out. So sy prime is just s y prime. Okay. Now again, I made the assumption S inverse existed, so let me go ahead and multiply S inverse to both sides here, and I get S inverse AS times Y is equal to Y prime. Now, this creates a similarity to what I don't know, okay? But again, having an invertible matrix, S inverse AS, does create a similarity because the product of this does equal some matrix. Okay, let's call this matrix B. And I now have this, which you might be thinking, yeah, but that didn't do anything, right? I mean, isn't this, for all intents and purposes, the exact same thing I wrote originally? And yeah, it is. The difference is, what I've done by rearranging these variables by a bit is that I've rewritten my original system. Instead of using the collection of coefficients in A, I get to use the collection of coefficients in B as long as there's similar matrices. But think about what would happen if my coefficient matrix down here, B, if it were diagonal. Well, if it were diagonal, this value would be 0, wouldn't it? And then instead of this first equation reading like this, it would read x1 prime equals 9x1 plus 0x2. Well, that eliminated a variable from my first equation. It's no longer a system in two, it's just two separate differential equations. As long as B is diagonal, this unravels my system of differential equations into separate independent differential equations. Okay? Now, granted, not in the variable I'm looking for, but we'll get to that. Okay? All right, so I know how to do this. I know how to make a B which is diagonal. I got to use the eigenvectors and eigenvalues. Now, again, I'm going to write those down for A because, again, you guys know how to find those. Okay? The eigenvalues are, oh, my notes. Here we go. 3 and -1. So here we go. So 3 and -1. Okay. And my eigenvectors are, for 3, it's -1, 1. For -1 here, my second eigenvalue, it is -3, 5. Okay, so let's see if we can't unravel what this means for this. It means that I can take this system, which is this, and I can rewrite it as B times Y is equal to Y prime. And again, what was B? B was the diagonalized version of A. It's the matrix with just the eigenvalues as its diagonal entries. So I'm going to do that now. Okay? I'm going to do that now. Let me go back. Okay. So here we go. Okay. So I'm going to go ahead and let me let X equal S times Y. And I know that S, well, I know what S is now, right? S is the matrix with these vectors, the eigenvectors, as its columns. Okay? So -1, 1, and then -3, 5. Okay, so there's S. Okay, so what I know then is, I know that if this is true, then what I get is that B times Y equals Y prime. And again, B was the diagonal matrix with the eigenvalues on the diagonal. Yeah, so B times Y equals Y prime. Now, of course, again, when I say Y, I mean the same thing I meant previously, which is to say that this is a variable vector. So when I actually say that, what I really mean is Y1, Y2. okay? And y prime is just y1 prime, y2 prime. Okay, and if this relationship holds, well, let's see. Multiplying row times column, that's 3 times y1, plus 0 times y2, that's 3y1, is equal to, well, y prime. Row 1 times column 1 gives me row 1, column 1 value, y1 prime. Okay? Row 2 times column 1 gives me row 2, column 1 value, so 0 times y1 plus negative 1 times y2, that's negative y2 is equal to y2 prime. And what I've now done is I took a system here, okay? I took this system here, and I've rewritten it. This system has become this system, okay? But these equations aren't mixed and matched. They're separated, okay? And I can solve them individually. Now, you should note these are both first order linear differential equations, right? 3y equals y prime. Again, I trust that you can solve these differential equations. If not, look back in your book in chapter 1 and look for first order linear differential equations or separable differential equations. This actually applies to both. Okay, regardless, I'm going to write down the general solutions for each of these, okay? So here I have y1 of t, again, I told you I was going to use t as my independent variable, is equal to some constant, call it c1, times e to the 3t. Okay, and it makes sense if I try to plug this back in. If I take the derivative of this, I just get 3 times c1 e to the 3t, which sure enough is just 3 times my original function, so it works. Okay, same principle here. I'm going to let y, here's y2. Again, still first order linear, still separable, everything's fine. And this is going to be some constant c2 times e to the negative t. Okay? All right, fantastic. Now this, of course, is not my solution. Okay? Because nobody asked me to solve for y, they asked me to solve for x. Well, yeah, but x is just s times y. Or, more appropriately, x1, x2 is equal to s, which is negative 1, negative 3, 1, 5, times y. Well, the vector y is just y1, y2. So this is c1 e to the 3t, c2 e to the negative t. Am I getting too small? We can read this. Okay. All right, so of course, again, doing the same thing with this matrix multiplication. Again, this is the 1, 1 entry. That's row 1 times column 1. That leads me to x1 of t is equal to, let's see, negative 1 times c1 e to the 3t plus negative 3 c2 e to the negative t, right? So again, row 1 times column 1, okay? x2, that's the 2, 1 entry. Take row 2 times column 1, so x2 of t. This one's equal to, here we go, we've got 1 times c1 e to the 3t plus 5 times e to the negative t. And there we go. Now we've solved our system, okay? Okay, so again, understood what we did here. We took this diagonalization idea and we were able to take a matrix which isn't diagonal, and while we can't make this matrix diagonal, I mean it's only equivalent to itself, it's only equal to itself rather, we can again define a similarity to something that's diagonal. And then in this particular case, again the algebra happened to work out here, this allows me to take, let's say, a system and unravel that system. Okay, so this is fantastic and a fantastic application of eigenvectors and eigenvalues. Now, you might be wondering, well, what if the matrix was defective, right? So this one happens to be non-defective. What if it's defective? And for that, for the things like that, we use something called Jordan canonical form. There's a section in your book, although it's not part of our syllabus, so we won't be covering it. But you should look that up. It's kind of enjoyable. Okay. As normal, I will put the homework online, and if you have questions, of course, you can ask it at our weekly meeting or semi-weekly meeting. We haven't decided the number yet because I'm recording this before we're getting started, but still, any of those things are okay. All right, again, make sure you practice, and good luck, guys. All right.